This lecture gives an overview of differential equations. So what is a differential equation? Remember in Calculus 1, we learned how to find the derivative of a function, right? Which is the instantaneous rate of change of a function with respect to an independent variable. So if you give an f of x, then in Calculus 1, you know how to find f prime of x. All right. Or if you call f of x as a y, as a dependent variable, then you're finding y prime, right? Or another way to notate it is dy over dx if x is the independent variable. But then when mathematics is applied to real world problems, it's oftentimes that it's easier to find the relationship between the functions and its rate of change or its derivatives. It could be the first derivative or second derivative, so on and so forth. So it's easier to find a relation between the functions and its derivatives rather than finding the formula of the function itself. So the relations between an unknown functions and its derivatives produces a differential equations. So let's say you have a you can find the derivative of y prime as a function of, let's say x is the independent variable and y is the unknown function itself. So once you can come up with a relations between the unknown functions and its derivatives, could be first derivative, second derivative, then that is when you found a differential equation. Okay, so this is a differential equations. All right, well, let's look at the first example. Biologists usually study the growth of a populations, right, of a certain species with the size at time t given by the functions p of t. So p of t is the populations at time t. They might be able to make an assumption, a simple assumption, but logical, that the population grows at a rate directly proportionally to its size, right? So it grows at the rate that depends on the size of the populations at time t. In mathematical notations, you can rewrite the equation for the population p of t in terms of differential equations. You say the rate of the populations with respect to time equals to r times p of t, where r here is the constants of proportionality, okay? And you can estimate r experimentally by working in the field, right? They're collecting the data, or from their own knowledge, they can estimate the r. All right. But then keep in mind that in real life, the equation that used for population growth can be much more complicated because there's more factors that can be involved in the process of a species populations growing, right? Such as weather can be one of the factor, or the interactions between populations, right? Or the interaction with different properties and the interaction with different habitats. So those factors can play a big role in the population growth. Again, this equation here is just a simple equations that you can use to estimate the population growth. Let's look at the second example. Physicists, right? They might argue that all the forces acting on a particular moving body at time t only depends on its positions and its velocity. So an object is moving, and what are the forces that apply to that object, the moving object. So they argue that positions will play a big role, and also the velocity, at what speed the object is moving, will play a big role in determine other forces that is acting on that moving object. So then one can use Newton's second law, right, to express the mass time accelerations and write an equation for the x of t in the form. Again, x of t here is the positions of the object. So the mass times the accelerations equals to f, right? And f is the functions in terms of x of t and in terms of x prime of t. And remember, if x of t is the moving functions, position function, then x prime of t is the velocity functions. So in this case, f is a function of two variables, x and x prime of t. All right, and one of the best known equations of this type is the spring mass equations. So this is the general formula for the spring mass equations when you have m x double prime of t plus b times x prime of t plus k times x of t equal to f of t, where m is a mass of the object, right? B and K here are the constants, and they are, so B is the damping coefficient, and K here is a spring constants. Again, this is the spring mass equation. And then the function f of t is an external force that apply on the system. Again, x of t, in this case, is the positions of the spring at time t. So in this both example, the problem has been written in the form of a differential equations. So here's this one differential equations here. You can rewrite this as like b prime, right, equals rp. Okay, and you know that t is the independent variable. Okay, and then in this equation you have an equation, a differential equations, where you have the second derivatives, right? You have second derivative, you have the first derivative, and you have the function itself. It's forming an equations. All right, and these two equations here will help us now solve the problems that we investigating. Well, in the first example, we just want to know what is the population of a certain species, P of t, in at times t, right? Finding P of t. Okay, and then in the second example, we just want to know the positions of the spring as time t. So you want to finding x of t. Okay, so the solutions to these equations here are to find what is P of t, what is x of t, right, which makes the equations true. Now let's talk about some of the basics terminologies in differential equations. First, a formal definition of differential equation is any equation that involving an unknown functions and one or more of its derivatives. So we look at this example here. The first equations. This is the harvest population growth. Okay, and in these equations, you can see that P of t is the unknown or the dependent variable. T is the independent variable, and N and H are constant parameters. And in different situations, in different problems, you figure your constant parameters depending on your knowledge about the problems, or depending on like the previous evidence-based research, right? And you can determine the real parameters. So different problems will have different real parameters. Okay. Well, look at the second equations here. So the second equation has second derivative of x in terms of t, first derivative of x in terms of t, and the functions of x. Is an example of a spring mass equation. And again, x of t is the unknown or dependent variable. T is the independent variable. Well, look at the third equation here. Again, you have the second derivative of I, just I, and of functions in terms of t. And in this case, is an example of an RLC circuit showing beat. And I, again, is the unknown or dependent variable. T is the independent variable, and omega is a real parameter. Okay. Well, then we'll have to distinguish between, what is an ordinary and what is a partial differential equations. So by the definitions, in a differential equation, if the unknown functions only depends on one independent variable, it only has one independent variable, then the equation is called ordinary differential equation. Versus if the unknown function depends on more than one variable, which is one variable or two variables or three variables, then the equation is called partial differential equation. All right. For an example, this equations here is an ordinary differential equations is because the functions, the x of t is only depends on the t, right? You only have one independent variable, which is t. And usually people use ODE as ordinary differential equations. So t is the only independent variable. Versus this equations here, if you look at these equations, you know u is the dependent functions, right, variable. And this dependent functions here, this unknown functions here, depends on two variables, which is x and y. So x and y are two independent variables. That's why this equation here is a partial differential equation. And usually people use PDE for partial differential equations. All right. And I will just say t is the only independent, right, variable. And then in this case, you can see that x and y are two independent variable. Okay, so that's why the second equation is a partial differential equation. All right, next, the order of a differential equation. So by the definition, the order of a differential equation is the order of the highest derivative of the unknown function. Okay, if you look at this equation here, what is the highest derivative of the unknown equation? The unknown function is p of t. The highest derivative is 1, first derivative. So this function is the first order differential equation. Okay. If you look at the second equations here is a beat functions, beat equations. The highest derivative of I of t is 2. That's why this function is a second order differential equation. All right. The next terminology is linear versus non-linear differential equations. So a differential equation is linear if the unknown function and its derivatives can only appear in the equation multiplied by functions of the independent variable. So if you are a linear differential equation, you cannot have terms like x squared x cubed e to the x ln x sine x, etc. if x is the dependent variable, or as you know, dependent variable is the unknown variable that you've been expressing, right? Otherwise, it is a nonlinear differential equation. Okay, let's look at example number 6. As you can see that if you look at this first equation here, you see x prime and x appear in this equation, right? And it's just multiplied by functions of t, and in this case, t is -3 and t is 1. Okay, that means this equation here is a linear equation, linear differential equation. All right, now look at the second equations. Let's see, we have x prime, right? We have x times sine of t, which is fine. So just x prime and x and multiply by a function of t. Then this is also a linear equation. Look at the third equations here. We have x prime, which is good. How about e to the x? E to the x here is one of the violations, right? We know right away that this is not a linear differential equations. Okay, look at the last example here. Well, at first, you see that I have x prime equals to 2t. At first, it appears to be a linear equation, but if you rewrite this equations, it will be x prime equals to 1 over x times 2t. And at this point, you have 1 over x here, which is one of the violations. That means this equation is not a linear equation. All right. Now we can talk about solutions to a differential equation. First, what is the solutions? In analytic solutions of a differential equation, analytic solutions is a sufficient differential equation, like is sufficient differential functions, a function that has the derivative, right? If substitute into the equation together, the necessary derivatives make the equation an identity. That means it will make a true statements for all the values of independent variable or over some interval of the independent variable. Well, let's look at example number 7. You're given a differential equations and you want to show that this is a solution to this differential equations. Okay. I'll say if I want to verify x of t equals to e to the -2 is a solution to this differential equation, then what should I do? If x of t equals to e to the -2t, and then in this differential equation, I have x prime and x double prime, that means I need to find what is x prime of t. Well, x prime of t is -2 e to the -2t. Okay, and I also need to find x double prime of t equals to -2 is 4 e to the -2t. Well, at this point, I found x. I have x, I found x prime, I found x double prime. Now I just plug these 3 parameters into this equation. So in the equation, first I have x double prime, so I just bring the x double prime down here for e to the -2t, right? Okay, and then plus 3 x prime. So x prime is here, so I can just bring it down here. 2 e to the -2t. and then plus 2 times x, and x is here, which is e to the negative 2t. So you have 4, 3 times negative 2 is negative 6, plus 2, 4 minus 6 plus 2 equals to 0. Yes. So it satisfies these equations for any value of t. That means, yes, x of t equals to negative e to the 2t is a solutions to the dE x double prime plus 3x prime plus 2x equals to 0. Okay. All right, this is, again, this is x double prime, this is x prime, and this is x. All right, let's go to the next example. Well, you want to show that, again, the functions x of t here is a solution to this dE. Okay, and I look at these equations, I only need to find x prime of t. So let's start with x of t equals to 1 minus t squared 1/2. Then x prime of t equals to 1/2 1 minus t squared negative 1/2 times 2t. I just use chain rule, right? And then at this point, I can see, can I simplify anything? Yes, 2 and 2 gone. And I would have t, right, times 1 minus t squared, negative 1 over 2. Alrighty, so I have x prime equals to these functions. Now, does x prime equals to negative t over x? We'll see. So on the left side, I have x prime, right? So left-hand side, I have equals to t 1 minus t squared, negative 1 over 2. How about the right side? The right-hand side, I would have negative t over x. X is 1 minus t squared over raised to 1/2. And as you can see that, I can, oh, this should be negative. So one thing that I forgot up here is it should be negative 2 and it should be negative t. All right, again, using chain rule, don't forget the sign and that. All right, at this point, we'll see. Can I bring, and still I have negative t here. Can I bring this over here? So the left-hand side and right-hand side doesn't look exactly the same, but I can either transform the left-hand side or I can transform the right-hand side. Well, at this point, I want to transform the right-hand side. So I want to bring the denominator up to the top because I want to get rid of the denominator. So t, if I want to bring this up to the top, it will be 1 minus t squared. Instead of the positive sign, I change this to the negative sign. Well, at this point, you can see that the left-hand side and the right-hand side are the same. So this will make the left-hand side equals to the right-hand side of the equation. Again, this is the left-hand side, and this is the right-hand side that I'm talking about. So if the left-hand side equals to this right-hand side, then yes. X of t equals to 1 minus t squared 1/2 is a solutions to the dE x prime equals to negative t over x, which is what we want to show. All right, now we can talk about families of solutions and initial value problems. Well, let's consider a very simple differential equation, x prime equals to x. It is very easy to guess that one solution to this equation is e to the t, right? Because if x of t equals to e to the t, then x prime of t equals to e to the t. So that means x equals to x prime equals to x of t. Okay. Well, this is easy to see that, but it's not obvious to see that if you multiply e to the c to a constant c, where c is any value, any constant value, then this function here is also a solution to this differential equation. Because if you multiply so c to e to the t, then x prime is also c times e to the t, and again the equations is a true statement. That means x to the t equals to c times e to the t is also a solution. Okay, so that we're saying it because we have infinite many value for c. That means we just found a family of the solutions for this differential equations, or it can be called like a one parameter family of solutions because the constant c here is one constant parameter. Okay, for the first order differential equation, this is the first order differential equation. Well, in this case, we call that this function's x of t equals to c times e to the t is the general solutions of the equation x prime of x. Okay, it's a general solutions because c here is still unknown, and c can be any value depending on a particular situation. Well, once we have a general solutions, can we pick our single solutions? The answer is yes. You can pick out a single solution, or you can have a particular solutions if you can specify a point on the curve of the unknown function. Right, a point, if you can pick out a point on the curve of the unknown functions, which is called initial conditions, then you can find a particular solutions. And usually this point here, this specific point here, can be in the form, well, x of t0 equals to x0, or you have a point t0, x0. Is one specific point on the curve of the unknown functions. Okay. Well, that leads us to like general solutions. Particular solution will lead us to an initial value problem. So a first order differential equations, if you have the first order differential equation, and if you have one initial condition, then you have a initial value problem, IVP, as the abbreviations of initial value problem. And then the solutions to an IVP will be called a particular solutions of the differential equations. So you have the first order differential equations, you have an initial condition, then you have an IVP. And when you find the solution for this IVP, then you have the particular solution to the differential equation here. All right, let's look at the next example. Again, we just using this simple functions for now. And in this case, we have a initial value, okay, x of 0 equals to 1/2. What does it mean? That means when t equals to 0, x equals to 1/2, okay? Or in some other, using a different notations, some can write 0, 1/2. And you still understand that when t equals to 1/2, t equals to 0, x equals to 1/2. Okay, Well, we already know that this is a general solutions, right, for this differential equations, and now we have an initial value. Then we just need to plug 0 into t, 1/2 into x, and you solve for c. So 0 into t, e to the 0 is 1. So the right-hand side would be to c, and x into 1/2. That means c equals to 1/2. So once you found c, you can plug c into your general solutions to find the particular solution for this IVP. So this problem here is, this is an IVP problem. When you have a differential equation, the first differential equation, and you have one initial value, then you have an IVP problem. And you found the solutions. First, you found the general solutions, then you found the particular solution for this IVP. All right,